Welcome to the third video in this sequence of work solutions for Edexcel GCSE Computer Science. In this video, we're looking at Paper 1, question 1b. We'll go through the answers to that. That was converting binary to hexadecimal. And then your challenge is to have a look at question 1c, which is about logic gates and truth tables. So let's have a look again at the question that you saw in the previous video, which was converting binary to hexadecimal. Let's read through the keywords and then work through the solution. So the first 6 samples in an audio recording for podcast 2 are shown below, and then we've got 6 4-bit binary numbers. And then it says convert that binary number, again it's the same 6 4-bit numbers, to hexadecimal. This question's worth 3 marks, so let's talk through how to get there. First of all, we know that a bit is worth either 0 or 1. We call binary base 2 because it's only got 2 possible values that any digit can be. We need to convert to hexadecimal, which has 16 possible numbers. We're used to counting in denary. Denary is base 10. It's what we're taught from primary school onwards. It's where you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10 possible values for any digit. We know in binary that if you have 4 bits is 1 nibble, and then 8 bits is 1 byte. So we've got here 3 separate bytes of binary, or 6 nibbles. Now the trick if you're converting to hexadecimal is only ever to do your conversions with 4-bit binary nibbles, because it works really nice and easily to do your conversion. The way to do it is to take your first binary number, so the first binary nibble, write it out, 1011, and then remember, starting on the right, the least significant bit, the bit worth the least, that bit is worth 1. And as you move to the left, if it was denary, it would be worth 10 times as much, to go tens and hundreds and thousands. If it was hexadecimal, it would be worth 16 times as much, but we're in binary, so it's just worth twice as much. So 1, 2, 4, 8. Each bit is worth twice as much as the one on the right. Then to work out the denary value, if you've got a 1, you just add the number above it to find out how much it's worth. So here we've got a 1 here, so that's 8. A 1 here, so we add that 4. We've got a 0 here, so we ignore that, but we add that 1 here. So this 4-bit nibble, 4-bit binary number, is worth 8 plus 4 plus 1, which 8 plus 4 is 12, plus 1 is 13. So this number is worth 13. Then we work on the next one. So 1, 0, 0, 0. You could do the same. So 1, 0, oops, sorry, written it the wrong way around. 1, 0, 0, 0, 1, 2, 4, 8. And then we ignore all the zeros. This number is just worth 8. Now I'm not going to write out the bit value for all of these. We're just going to look at what we've already written out. So we've got an 8, we've got a 4, we've got a 2 and a 1. Add them all together, you get 15. Here we ignore the 8, the 4, the 2, and we just have a 1. Here we've got 1, 1, 1, so we've got 8 plus 4 plus 2, but we haven't got the 1. If you add 8 plus 4 plus 2, you get 14. And then we've got 8 plus 1 is 9. So each of these binary nibbles, we've worked out the denary value for them separately. So we're halfway there now. The last step to do is any number bigger than 10, as in any number that needs more than 1 digit to represent it in denary, we need to convert into a letter. So I'd always recommend writing out from A onwards. So remember, in hexadecimal you can have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, like you can in denary, but you can also have A, which is worth 10, B, which is worth 11, C, 12, D, 13, E, 14, and up to F, 15. I would always recommend writing out this little table in a hexadecimal question. It only takes a couple of seconds and it just avoids you making any mistakes. Then we've worked out that 1101 is 13. So you look at your table and 13 is D. 8 is only 1 digit, so it's 8 in hex as well. 15 is F. 1 is only 1 digit, so it's the same in hex. Here, I can't read what I've written here, so let's just double check. So 8 plus 4 plus 2, 8 plus 4 is 12, plus 2 is 14, 14 is E, and then 9 here. Okay, so we've gone from 4-bit binary numbers into 4-bit hex digits, and one 4-bit nibble is one letter, one character in hex. 3 marks available. You get 1 for D8, 1 for F1, and 1 for E9. Okay, hope that's useful. Let's have a look at the next question. So your challenge before you watch the next video is to have a look at this question. This is question 1c. You've got 3 logic gates here. You've got an AND gate, an OR gate, and a NOT gate. You need to make sure you understand the symbols to know which are which. And you've got a truth table to complete. So a truth table means you know what the inputs are, and you need to determine what the outputs are. So let's have a look. We've got 1, 2, 3 inputs, A, B, and C. Those inputs can be zeros or they can be ones. So let's have a look at this first row. This says A, so this row here says A is a 0, B is a 0, C is a 0. You'll have to go away, find out what the logic gate symbols are. It says that D is a 0, that E is a 1. You have to work out what F is and write your answer in here, and then do the same for all of the gaps. Okay, hope this has been useful. All the best for your revision, and I'll talk you through the answers in the next video.